section 3.1 and 3.2. So in these sections, we are going to talk about determinants and their properties. So determinants is one thing is only for square matrices. So what is a determinant? It's basically a number associated with the matrix. A real number, if we have entries of the matrix are real number, then the determinant will be a real number. 2 by 2 matrix. Now this is another notation for determinant. This is the one that I showed you before. So sometimes you will be given evaluate. So something like this: 3, 2, -1, 0, 4, 2, and 1, 5, 0, for example. So if the bars are given here, it means the question is asking you to find the determinant. So remember, this is different from notation is different from the notation for the matrix, because for matrix we have the square brackets. Here we have straight lines. So be careful. If you put square lines, something like this, and we try doing AD minus BC, will be wrong, because determinant and square and the matrix are different things. Okay. We already know how to find the determinant of a 2 by 2 matrix, and then how to find the inverse of a 2 by 2 matrix. So here we will start with the case of a square matrix and of order n by n, where n is greater than 2, and try to see how we can find the inverse of that matrix. The method that we are using here is, we call it the method of minors and cofactors. And so first thing is, what is a minor and what is a cofactor? Well, minor is, we denote it by Mij. By the way, the minors and cofactors will be calculated, or must be calculated, for each and every entry of the matrix, or whose inverse we are seeking, because for the inverse we need all the cofactors. But for the determinant, we need only maybe for one row or one column. So what is a minor? It is a determinant which is obtained by omitting the ith row and the jth column. So for every entry, as I said, there will be a minor. So if you are trying to calculate the minor for A22, whatever size of the matrix, you have to omit the second row and the second column and write the rest of the entries. So what is the cofactor, which is denoted by the Cij? It is just a sign, putting a sign in front of the minor. Sometimes the cofactors will be exactly the same thing as the minor, and sometimes they will be the opposite of the minor, depending on the sign. Now here the formula is saying that -1 raised to the power I plus j, which means whenever I plus j is an odd number, you'll get a negative sign. Whenever I plus j is an even number, you get a positive sign. So, but we will not get into this. I will show you another way of picking up what the sign is going to be. And we are not going to calculate the minors separately and then cofactors separately. It will be too much work. So we'll just go by this trick of putting the sign in front of the minor to make it a cofactor. So we will be directly calculating the cofactors. Here are some, formulas, you can say, for finding the determinant. So we can use any row or any column of the matrix to find the determinant using any row or any column. And the formula will go, if you have the ith row, so it will be go AI1, CI1. So you take the entry of that first entry of that row and multiply it by its corresponding cofactor, plus the second entry of the row multiplied by its corresponding cofactor, and so on until we get the last term of the row and multiply it by its cofactor. And similarly, it works with the columns. We will mostly use, well, again, it depends on which row or column we are using. So what we do in finding the determinant or in finding the inverse as well, so we will be using the row which has most zeros. That will be helpful. Keep that in mind. Okay. So what is the inverse of a n by n matrix in this case? The first thing is something we call adjoint of a matrix. So what is the adjoint of a matrix? This is where we need all those cofactors that we calculate for each. So note here that if we have a matrix of size 3 by 3, there will be 9 cofactors that you will be evaluating. If it's a matrix of size 4 by 4, there will be 16 cofactors and so on. If it's a 5 by 5, well, depending on how we tackle it, okay. It's not always that you have to do 5 by 5, 25 for a 5 by 5 matrix. We may not have to calculate 25 cofactors. We will see that in a few minutes. Okay, so then now A inverse will be 1 over determinant of A times adjoint of A. But what is adjoint of A? So this is the one we put our cofactors, but notice here the order is kind of, it is actually transposed. So normally we will say, okay, A11 comes over here, so this should be C11, it should be sitting here. A12 comes in this place, so C12 should be coming there, and so on. So C13 should be here, and then C21 should be here, C22, C23. If we just put them in their corresponding positions of the entries for which we calculated the cofactor, C32, C33. But the adjoint is the transpose of this. So if you notice here, C11, C12, C1n, C21, C22, C2. So the rows of this matrix are the columns of the adjoint. Okay, let's see how we do the example. So, but before that, as I said earlier, trick to remember how to remember what the sign will be for the corresponding cofactor. So if it's a 3 by 3 matrix, we always, no matter what size of the matrix is, the first entry of the first column of first row is always going to be positive. So we are going to start with a positive sign. Now, if you can go right or you can go down. You cannot go along the diagonal, okay? Don't go along the diagonal. So, but if we go to the right, so counting positive, negative. So remember there are 9 entries. So we will go like this. So this is positive. Let me use another color here. So it becomes clear. Okay. So we will have positive, negative, positive. And now because there is no more in that row, now we come to the second row over here. Actually, we can continue here as well. Negative, positive, negative, positive, negative, positive. So, or you can go in any way. We could have started from here, positive, negative, positive, negative, positive, negative, and then go down. Or you can go like this, positive, negative, positive, negative, positive, negative, positive, negative, positive. Here is the breakdown for the 4 by 4 and so on. So this is how we can do the sign, and so calculate our the cofactors and then use this formula, this one, to find the inverse. Okay, so here is an example. Find the inverse of this matrix. I'm giving it a name A. And so we have to find the inverse of it. So we start here by calculating the cofactor. So C11. So remember C11 because it's coming in the A11 position. So for that, the minor will be written by omitting the first column and the first row. So I have negative 1, 2, 0, 1. Now when you are doing it, don't put lines on the columns and the rows, because then you won't be able to erase them. Then it will become, and numbers get hidden or crossed and we cannot see them clearly, because for me I will be erasing them or going backwards, so removing them. Okay, so this is my C1 2. So I'm going down here. If you notice, I'm going here in this direction, because that's how we will put them in our adjoint matrix. So then the C12, although C12 is the my minor or cofactor for this place, but when we calculate it, we have to think of omitting the second column and the first row. So we get 6, 2, 4, 1, but the sign will be negative. Why? Because the first one is positive. So then second one is negative. Then we will look at the minor for this one. So the sign will be positive. So I have a plus here. And then the matrix 6 minus 1, 4, 0, which we get after omitting those line and row. Okay. The next is we calculate these, all of them. So once I have all the minors, and then I do the calculations and I get all the minors here now. So the next thing is to find the determinant. Okay? Next step is to find the determinant. So this is kind of step 1. This is step 2. And then we will do the step 3. Step 3. Step 3. Okay? That is the last one. Okay. So how do I find the determinant? Again, it's your choice which row or which column you want to use. I think I use the first row. There is one entry 0, so we have basically just 2 terms to calculate. So determinant of A will be 0 times the cofactor which is associated for this position, which is C11, so which is negative 1. So 0 times negative 1 plus 2 times C12. So 2 times 2, and then plus 1 times C13, which is 4. So we end up getting 8 as our determinant. Okay. Now we come here in the third step. So what is going to be my my inverse? So this will be, this was a 5 here, for some reason it got erased. Okay, so A inverse will be equal to 1 over 8 times the cofactors, the adjoint, which is the matrix for cofactors, filled with cofactors, but then transposed. So the cofactors that I found, I just pick them. This make it first column of the matrix. Pick the cofactors here. This is equal to 8, which I am writing here. But now I will pick this and put it in the second column. And then in the same way, I'll pick these and put them in the third column. So, and then 1 over 8 is. Now you can compare it with the inverse of the matrix that we calculated in section 2.2. It was the same matrix as I have here. And this will, you'll see that we got the same inverse when I pulled out the 8, the highest, greatest common divisor. And if you multiply this whole matrix by 1 over 8 and simplify, you will see that we get the same answer that we got in that example in 2.2 with the fractions. Okay, so let's look at this next example, which is, I gave it the name B, so now we are looking for determinant of B, or you can just start with this over here. What I did, I wrote all the entries, but now I have my bars around, so not the brackets. So this means I am calculating the determinant. So I can start with the first row, but then can you see it will be so long. If I start with the first row, then I will get a minor which will be a 4 by 4 matrix, then with 3, 2 for all of these 4 by 4 matrices, and then each 4 by 4 matrix will be converted into 3 by 3 matrix. So it will be very long. So what we try to do here, try to find a row or a column with maximum number of zeros, and luckily here we have this fourth row which has 4 columns. So we immediately grab that and we say, okay, this is the one I'm using to expand my determinant. So the first thing you have to know or get is the sign, what sign will come. So we start, as I told you before, plus, minus, plus, minus. So we'll have a negative sign, so I put -2 times. So this is the Aij, right? So in other words, it is the A41. So the value of A times the sign because of the minor, and this is the minor. Okay? The minor is obtained by omitting the 4th row and the first column. So the rest of it is coming here. Okay, once we got, but the rest of them are 0, so that is just the only thing I get. So I am now getting only one 4 by 4 matrix. Then we try to see if there is another row with bunch of zeros or a column. So we notice that we have a 4th column. There are 3 zeros and only 1 entry non-zero. So we can use that. Again, we have to do what is the sign going to be. So it is -2 times this quantity. So again, positive, negative, positive, negative, positive, negative. So this also has a negative sign. So I go -2 times -1 times the minor for this entry. What is this position? 4, 4, 4, 3. Sorry, 3, 4. Third row and fourth. Again, it doesn't matter because we just know that we have to omit this last column and the third row in which this entry is lying. So we'll put the rest of them here, and this makes it the matrix. And now it's easy to expand this 3 by 3 determinant, but still we can use a row or a column which has at least 1 0 in there. So I notice that the first column has a 0, so I'm going to use that. So the -2 times -1 is giving me 2 now, and then because we are getting only 1 0 here, so there will be 2 smaller determinants or minors, so there will be 2 terms. So I'm putting a bracket here because the whole thing will be multiplied by 2. If I don't put a bracket, I might not get I will not get the correct answer because I might forget to distribute the 2. That's why the bracket is needed. Or you can put parentheses if you want. If you think this will be confusing, bracket will be confusing because of the matrix, so we can put big parentheses around here. So when I do it, again we are going to use that cofactor thing for expanding the determinant. So it goes like, okay, the first, whatever we are using in this case, the first column. So the first entry of the first column times the cofactor for this position. So the cofactor will consist of the elements or entries which are not in the first column or and the first row of this determinant. So I get the minor is 4, -1, 3, 2. And the sign here is, notice that positive because of the first entry. Okay, then we come here, but there will be a negative sign, so -0 times, although we don't need to write this term because we know it will be 0, because 0 multiplied by determinant is 0. But anyhow, just to make sure that you understand how to do this, because the next will be plus, so positive 2 plus 2 times the minor. And now we just expand. So I still have 2 outside and the big parentheses. Then 3 times, now this minor will give me 4 times 2 is 8. 8 minus negative 3, so 8 plus 3, which gives me 11. So 3 times 11 minus 0 plus, okay, plus 2 times. So this is plus 2. And then when I do the inner thing, I get 2 times negative 1, negative 2 minus negative 16. So negative 2 minus 16, negative 2 minus 16, which gives me negative 18. That's what I have here. Multiply 33 minus 36, and we have 2 outside, so we end up getting 2 times negative 3, which is negative 6. So this is your determinant. Okay. Now when we have a triangular matrix or a diagonal matrix, it's very easy to calculate the determinant. You just multiply the entries in the diagonal, the main diagonal. And remember, the main diagonal we discussed before of a square matrix will be the one which goes from the A11 to the ANN. So I just wanted to mention, because previously I haven't used this terminology, triangular matrix. So what is a triangular matrix? So a matrix in which all the entries above the main diagonal are 0, or all the entry below the main diagonal are 0. These are triangular matrix. And to be more specific, the one in which all the entries above the diagonal are 0, the entries below the diagonal, at least one of them is not 0. We call it the lower triangular matrix. And the one in which there are all the entries below the main diagonal are 0, but the entries above may not all be 0, is called the upper triangular matrix. And then if A is a triangular matrix or a diagonal matrix, then determinant of A is the product of the entries on the main diagonal. You can use row operation. This is another way of finding the determinant of a matrix. Remember, we have already seen one method, which is by using the cofactors. But this one says that you can reduce, or reduce your matrix or convert your matrix into the echelon form, and then which is a will be an upper triangular matrix. So then you just multiply the entries on the diagonal. Okay, you can use row operations to make the most entries 0 in a column or in a row, and use that column or row for cofactor expansion. So to always remember, again, as I mentioned earlier, to find the determinant, use the row or column that has most entries 0, because that reduces a lot of work. Okay. Now this example is saying find the determinants of the matrices A and B given above. Which ones? The ones I just showed you here, A and B. So what will be the determinant of both of them? If you notice, we have some zeros in the diagonal. So because the determinant will be just the product of the diagonal entries. So 1 into 0 into 3, so 0. And for this one, 6 into 0 into 6 into 0 into 5, so that will also be 0. So the determinant of this one is 0, and the determinant of A is 0 because of the product on the of the entries on the diagonal. Okay, now that we have learned how to find the inverse by two methods, we will now see how we use it. So here is a theorem which says if A is an n by n matrix, invertible matrix, then for each B in Rn, the equation Ax is equal to B has a unique solution and the solution is given by X is equal to A inverse B. Why and how? Well, this is something you should be able to figure out because of the examples we did at the end of 2.2. So given equation is A, X is equal to B. I want to get X by itself. I want to isolate X, which means I have to get rid of this A here. So how can we do that? We cannot divide by A. Remember here, matrices, we never talked about division. But I can get rid of this A by multiplying on this side by A inverse. So that's what I do here, A inverse times A. But then I have to do it on the right side as well. So I do it on the right side. So the left side gives me I, identity matrix, I'm X, is equal to A inverse B, which gives us X is equal to A inverse B. That is what we have here. So how do we do this? So we are given this example. So use the inverse of a matrix. Use the inverse of a matrix to solve the system of equations. So we are not going to do the row reduce, echelon form. We are using the inverse. So whose inverse? Well, you should know that as it's saying here, A inverse. So what is A? How do we get A? Recall that the system of equations can be written in matrix notation like this, where you know the matrix of coefficient is the A matrix, then the unknown is the X matrix, and the B is the matrix on the right side of the equal signs. So our A is 2, -1, 2, 1, and now I need to find the determinant of this. The determinant will be, remember, 2 minus -2, so it will be 2 plus 2 is equal to 4. So the A inverse will be this quantity. Remember how we find it? We swap the main entries on the main diagonal, we swap them, and then the entries on the other diagonal, we change their sign. So this is what I am getting. And we can multiply by 1/4 each quantity, but I think it will be easier if we leave it like this. So now we have to find our X. So X is A inverse times B. So A inverse is this, B is that. I put it there. I now multiply this matrix with the vector here. This is how we multiply. We go left to right in the first matrix and top to bottom in the second. So when the first row is multiplied with this column, we get -3 plus 7, which is 4. So I have a 4 here. And when I multiply by the second row and the column matrix, I get -6 plus 14, which is 8. That's what I have here. So now 1/4 times 4, 8. Now we can multiply by 1/4. So we end up getting X is equal to 1, 2. So here I am writing like values of x1, x2 separately, or you can have the answer in this form, in the vector form. So I think sometimes it's easier to do it, to solve this this way. Okay, last thing we talk about is some properties of the determinant. So it says that A and B be square matrices of order n by m, and then A is invertible if and only if determinant of A is not equal to 0. So any n by n matrix, it will be invertible if the determinant is not equal to 0. If the determinant is 0, then that matrix cannot be invertible. Now, determinant of A is the same as the determinant of transpose of A. Or in other words, determinant of transpose of A is the same as determinant of A. Then if you have product of two matrices, and so you find the product and then you find its determinant, you will get the same answer as if you found the determinant of each of those matrices and then multiplied them. Now, if B is obtained from A by adding a multiple of one row of A to another row, then determinant of B will be just equal to the determinant of A. And the fifth property, that if B is obtained from A by interchanging two rows of A, then determinant of B will have a negative sign in front. So it will be equal to negative of the determinant of A. And number 6, if B is obtained from A by multiplying one row of A by a scalar, then determinant of B is equal to K times determinant of A. So let us look at some small examples there. So let A be this one, and then we know that determinant of A is negative 3. You can calculate that. Now we are saying find the determinant of B if B is equal to transpose of A. So we write B here. So we transpose. So first column becomes the first row here, and the second column becomes the second row. Now when we use AD minus BC on B to calculate the determinant of B, we get negative 8 minus negative 5, so minus 8 plus 5, which is negative 3. So what did we notice? That determinant of A and determinant of B are same. That's what it said in the property up there. Second part, B is obtained by multiplying second row of A by 2. So we multiply this row by 2, which is going to give me this new matrix B, and the determinant of B will be now negative 6, which is 2 times negative 3, which means 2 times the determinant of A. So what you see, that's what the property says. And similarly, B is obtained by multiplying second row of A by 2 and adding in the first row. So when I multiply the second row of A, so this was the second row of A, add it into the row 2, 5. So what happens? I get a 0 in this position and negative 3. Now calculate the determinant. We get negative 3, which is the same as the determinant of A. And last one here, B is obtained by interchanging first and second row. So if you interchange and calculate the determinant of B, you will end up getting a 3, which is negative 1 times determinant of A, because determinant of A was negative 3. So we get a different sign, opposite sign. Last thing, let A be a square matrix, then determinant of A is 0 if an entire row or entire column of A consists of zeros. So you can check this example. If you expand, you will see that you end up getting a 0. 2 rows or columns of A are equal. So here I have another example, 2, 3, 5, 1, negative 1, and 2, 3, 5. So if we expand, you will see that you end up getting a 0. And then the third thing, one row or column of A is multiple of another row. Okay? So here I have the third row is multiple of second row. So the answer will be 0. So these properties are that without calculating the determinants through that long process, you can use these properties. If you see in a matrix you have a row of zeros, then you can just say the determinant will be 0. It is singular. You cannot find its inverse, and so on. Okay, that's all for chapter 3. We will move on to chapter 4 after doing section 2.3.